Good afternoon. Um, this is Han from Riken, Japan. Thanks to Professor Young Hoon Chu and General Chair of CSW and all the committee members for inviting me. Today I would like to talk about the advances and challenges in transparent AlGaN UVB LEDs. I also updated the author list, so please check carefully. Here is the outline of my presentation. I will briefly talk about the background and then a wide range of application of UV LEDs and current status of the AlGaN based UV LEDs, a result achieved so far. And they are discuss about the recent challenges of transparent AlGaN based UV LEDs, especially differential resistance, high operating voltages, and efficiency droop. And then I will share our result by replacing the p-type multi-quantum bare electron blocking layer with undoped aluminum graded electron blocking layer, which was found useful. Then I'll summarize my talk, and then also I will briefly propose my future roadmap against the challenges of the transparent UVB LEDs. I think everybody knows that mercury pollution from fluorescent lamps or UV lamps is a very serious issue, and World Health Organization declares the top 10 chemicals which are health hazards. So these are the chemicals. So we need to carefully trash the tube lights and the others conventionals mercury-based light sources in careful way, because it's very toxic and can cause a lot of health problems. Why big no to mercury and CO2, but not no to AlGaN or aluminum nitride or gallium nitride? Because mercury, the conventional LED lights or UV lights is based on the mercury lamp. But mercury is very toxic because methyl mercury was discharged in Minamata Bay in 1950. It causes a lot of human losses and many were disabled. So UV mercury lamp are highly toxic. Therefore, Minamata Convention was signed in different time, but in 2020 they come up with a very conclusive decision to replace the toxic mercury lamp. Also, CO2 is a very serious emission, a serious problem. Just for example, lighting just one room in every house with LED instead of a fluorescent lamp, one can reduce CO2 emission by 1 billion tons per year. So these are not good sources of light. But if we go for AlGaN or GaN or AlGaN based LEDs for different lighting sources, for UV sources, so we can reduce a lot of environmental pollution, for example CO2, and we can stop using mercury materials. So pollution caused by chemical pesticide or others toxic chemicals. So we need to protect present and future generation from these hazardous chemicals. Currently, there are over 350,000 chemicals and mixture of chemicals registered for commercial production and use worldwide, and some news are coming into market. So to regulate, some people are regulating, some people are not regulating. It depends state by state and continent by continent. That's a very serious issue. We have to carefully use different chemicals, or if you can avoid the chemical, would be great. Here is just one example. In 2019, 99% of the world population was living in places where the World Health Organization strictest zones, the air quality guidelines were chosen by World Health Organization, but most of the countries were unable to meet the guidelines. So those, you can see that how the intensity of those air quality changing across the globes. So the Norway and some other EU countries are better, even including Japan. So they have under 13 microgram per meter cube. So this is the air quality of the like PM 2.5. So we have to be careful about those concerns. And another concern, which is very, in my opinion, is very serious, because mostly developing countries and underdeveloped countries, their economy is based on the agriculture, and especially they are using a lot of pesticides, and pesticides have the potential to contaminate air and affecting the health of humans, not only humans but all the living things in the universe, and also degrading the quality of the soil. So by using but we have some solution for some part of the, I will talk about later, that's how we can replace some of the pesticide with UV light instead of using chemicals. So UV light is very clean source of inactivation of viruses, bacteria, and fungus, and also some others disease. We need a clean and green UV solution to protect human lives and nature from the adverse effect of viruses, bacteria, and other toxic environmental pollutants, including mercury and CO2. So in addition to all those issues, I will just talk about some potential application areas of the UV LEDs. So today I will not talk much about far UVC, but far UVC is of course very important for inactivation of viruses, bacteria in manned environment if you use far UVC. So from 190 nanometer to 225 nanometer is quite safe if you use in the presence of human, but about 230, so the TLV is terrible. We have a lot of application for water cleaning, but most importantly, the UVB light can be used for immunotherapy. Skin atopic dermatitis, like 311 nanometer is quite useful for skin atopics and vulgaris and cirrhosis and some others autoimmune. I mean the problem caused by our immune system in human body. On the other side of, if we consider the agriculture, so we can also suppress a lot of disease in agriculture, especially in the plants like powdery mildew of the strawberries, and we can also enrich phytochemical in plants if we grow under the UV light, and also we can suppress the tomato mosaic virus by UVB light. So as I talked before, so we have a lot of potential for UVB applications. For more detail, you can go to this wonderful book written by, and a paper and one book written by Professor Koneisel of Germany from the Technical University of Berlin, and some of the papers belongs to us. These are the few examples. If you see, that's the TOM-V by using 280 to 290 nanometer UV light was quite useful, but under the 217 it was not useful for TOM-V. It depends, depends of the viruses. This plant is without TOM-V. It was a normal tomato plants, and this is the TOM-V non-UV. So you can see that TOM-V with UVB light we can grow very healthy tomato. Without using any pesticide. So this is the useful aspect of the UV technology. This is the example that I talk about, the strawberry or some others plant a disease like mildew and mites, and which pose a significant threat to many crops, but one can sustainably reduce by using UV light. UVB light can be used for the vitamin D3 production. I got this cover later of the SSA by Physica Status Solidi A in 2019. The distribution of vitamin D3 in a population living about in some part of the Europe near to the Sweden. It was found that 23% of men and 17% of women, they are facing to the insufficient level of vitamin D3, and UV light can produce vitamin D3 in the human body, but we have to carefully use UV light. I will talk about this TLV, or like the guideline or the standard guideline for using of the far UVC and UV, all UV emission wavelengths for our human body. I will explain later. This is the how safe III-Nitride material based UV LED can be used. So if we go the 190 nanometer to 225 nanometer could be safe, even on human body, but about 230 nanometer up to 280 nanometer, it can cause skin cancer, and also the if high power, the LED about 280 to 320 nanometer, which is the bottom line, the border of the UVA, is also cause cancer or some others a problem to the human cells and tissues. But UVA is also can cause the premature skin aging. So what I was talking about, the American Conference of the governmental industrial hygienist recently took a step regarding the safe use of UV light, especially the threshold of ultraviolet-C light exposure. The TLV was enhanced in the 50 years record because of the new research and new development in on the clinical side, and they come up with a new. So you can see the previous far UVC TLV, the threshold limit value was like this, at 25 to 16 from 220 to 230 nanometer, but it enhanced to 218 for 220, and then 230 was 46 millijoule per centimeter square. And I will talk about the UVB later. Here is the UVB proposed limit of the exposure limits of the UV radiation. So here for 280 nanometer and 300 and 310. So the propose for eye use for any medical application, these are the recommendations to use the millijoule per, like 3.4 millijoule per centimeter square, and 10 for the 300 and 200. For 310 is we can use high. So this wavelength 310 is very important for skin atopic and some others disease. So so there was one just to share one of my magazine article which was published several years ago about the UVB LED refining the design. I will talk about the technical part of these news. So for all those wonderful application of the UVB LEDs, so we have still a lot of challenges to improve the external quantum efficiency and light output power and the full width at half maximum of the emission spectra. So these are the few challenges, like we have the poor crystal quality of the quantum well area, and then ultimately it causes low internal quantum efficiency. And also we have a problem with the low hole injection efficiency. Recently we could solve this problem by the aluminum graded p-AlGaN hole source layer, or can be solved by some p-type hexagonal boron nitride or magnesium zinc oxide materials, or to explore a new material for p-AlGaN, because to the quantum well the silicon doped electron source layer is quite enough, but the magnesium doped AlGaN hole source layer is not enough. So the number of electron going to the quantum well is quite higher than the number of holes coming to the quantum well for the radioactive recombination rate for the efficient light emission. And also for UVB, we are fine with those anisotropic emission, because the transverse electric field and transverse magnetic field, so the transfer electric field emission is more than the transfer magnetic field in the case of UVB. But for far UVC, we have this serious problem. So we need to improve the crystal quality and also the P layer for more hole injection, And another issue is the light extraction efficiency, which is caused by the total internal reflection of the light, and also poor the p electrode reflections. And also we can introduce several new ideas to improve the device structure. Well, I will just briefly share our achievement at Riken for the 275 nanometer. We got the world record data of 20% EQE, and recently for UVB 222, my group got 9.6% external quantum efficiency without using any lens or any package, just on bar wafer. But this was through the lenses and through some micro PSS, and but in my case, no micro PSS and no lens and no any thermal management was used, but just on bar wafer. And here is the far UVC achievement by our group at Riken. We are somewhere here, still long we have to go. This is the LED progress chart, including our results until 2023. Which is published paper. Sorry, I know some wonderful company come up with very good result, but I'm not talking about the company data. I'm only talking about the published papers. So these are if somebody interested, please go through those papers. How we go to the last high efficiency UVB LEDs. How we come to these high efficient UVB LEDs. So first we focus on the quantum well crystal quality. This is the quantum well structure, which is grown on the aluminum nitride template on C sapphire substrate. But we grow thick AlGaN buffer layer, which was 42% relaxed, and then electron source layer, which is 50% relaxed. And these kind of relaxation is very important to reduce the dislocation density in the quantum well. So we grow this structure until the final barrier, which was 6 to 10 nanometer. And this is the final barriers AFM, and we could see the step-in terraces. And this is the reciprocal sparse mapping. We'll confirm the aluminum composition and relaxation rate of the grown samples. And also the full width at half maximum of the XRD along 002 and 102 reflection was quite smaller values, around 311 arc second and 442 arc second. And we come up with quite low level of the screw type and H type dislocation density shown here. As a result, we got along with the Yamaguchi University of Professor Yamada, we got a very high internal quantum efficiency of 54% at room temperature. So this somewhere we improve the IQ, which is more or less really close to the predicted values by Shatalov and Ben, which has been shown here. So now how we improve the external quantum efficiency and also the light output power of UVB LED, because we introduce aluminum graded p-type multi-quantum barrier electron blocking layer, and also aluminum graded p-AlGaN whole source layer in UVB LED to improve the carrier injection efficiency, especially hole. As I talk about the quantum well structure, after the quantum well structure, we introduce those graded MQB structures, electron blocking layer 1 and 2, which was sandwiched. The value was sandwiched between the two electron blocking layer, and there was graded layer of the whole source layer was introduced here. And the top, excuse me, and the top, the P contact layer, we grow nickel aluminum P electrode, but the surface morphology of the P contact layer was again measured by the FM, and we still confirm the step-in terraces on the top. So the crystal quality was very good. And here's just example of the electron source layer and the multi-quantum barrier just interface. So we can get very good crystal quality and highly transparent also. This is the relative transmittance of the of the light through the device structure. So I will not talk about much. For more detail, we can go to those papers, scientific report, and the SCS publication, which was in 2020 and then 22, to how we go from the reference 8 to this scientific report improvement. So we introduced, as I mentioned, aluminum graded layer in the AlGaN whole source layer, and then electron blocking, multi-quantum electron blocking layers, EBL1 and EBL2, sandwich with the valley. So, and the aluminum composition was kept higher in the electron blocking 1 than the electron blocking 2. This is the experimental SIMS measurement data of the device. We just grow one reference sample with the aluminum graded p-AlGaN whole source layer and measure the electrical characterization by Wonder Power method, and we found that the resistivity was reduced to 24 ohm centimeter or 22, measured by two different equipments, and hole density was 2.9 times per 16 per centimeters cube. That's very improved result for us. Based on those new architecture, we can generate the three-dimensional holes in the whole source layer. So from here, and then those holes can go through the intraband tunneling, not only intraband tunneling, but also by thermionic emission to the quantum well. As a result, we got the experimental EQE of around 8.1%, by using the small reasonable chip size of 350 by 350 micrometer square area, and is the light output power also. But you can see we face this efficiency droop in those devices, and we also improve the device's structure by using super high reflective nickel aluminum P electrode, where previously we used 1 nanometer, but this time we use 0.4 nanometer, very thin nickel under the aluminum to reduce the absorption of UVB light. And we also check the numerically and analytically both the T and T mode of the reflectance as a function of the incidence angle, we found that the reflectance was quite enhanced around the incidence angle around the 60 to 70 degree. So as a result, if we use a small chip size, 250 by 250 micrometer square, we got a 9.6% EQE. And if you use a big chip size, then again we like 400 by 400 micrometer square, then we got 7.1% EQE, and the light output power was more than 39 milliwatt, but we still see this efficiency droop. So those efficiency droop was quite challenging for us. So we confronted with high efficiency droop, but at the same time high operating voltages in our previous devices. You can see that's a little improved operating voltage, but still very high. How to reduce those voltages from such high value, and also to suppress efficiency droop, we introduce a new structure. So previously we introduced a multi-quantum barrier electron blocking layer and then whole source layer, but this time we change the EBL just by undoped aluminum graded EBL, and then supported by p-AlGaN whole source layer, which was graded 2, very thin, and then p-AlGaN contact. But we still need to optimize the structure. But anyway, we also first we check theoretical simulation of this structure, and the simulation was done by using NextNano of German group, Dr. Stefano, thanks to their support, and we can get by undoped AlGaN electron blocking rather than multi-quantum barrier electron blocking layer. We can get very high hole density and also high radiative recombination rates in the quantum well. And the IQE, this time we can see the IQE. So there was no IQE droop in the thing. And because we were just to see those all to get the rough feelings of the EQE, so we tried to see the injection efficiency, how it's worked. We got very uniform as a current density. The injection efficiency was quite uniform if you compare with the MQB EBL. So based on those Neve model, we try to grow the devices for UVB applications. And here's the electroluminescence spectrum. But thanks to the Neve undoped aluminum graded EBL, so the operating voltages were quite low, even under 500 milliamps was like a 30 watt on bar wafer by using nickel gold electrodes. And the size was 400 by 400 micrometer. And the efficiency droop in the EQ was strongly improved. Of course, this is our first preliminary result, but we need to improve it. But it's very interesting that we got a very uniform EQE, I mean, very low efficiency droop until 500 milliamps. So if we make a package LED with proper N and P electrode and also lenses-like structures and others, thermal management, we can get very high efficiency. So let me summarize what we received recently. So by using 49% AlGaN electron source layer under the quantum well of UV LED, a remarkable IQE up to 54 and 57% was improved, and hole concentration of 2.6 10⁻16 with very low resistivity to 24 ohm centimeter in aluminum graded polarized p-AlGaN hole source layer for UVB LED was achieved. And EQE of 9.6% at emission wavelength of 304 nanometer with light output power 3 milliwatt at very small current of 10 milliamps by using a small chip size of 250 by 250 micrometer square. And by using a big size chip, 400 by 400 micrometer square, we can get more than 40 milliwatt on bar chip. But we can make a very high watt class UVB LED by using these architectures. And finally, the operating voltages were greatly reduced from 80 volt to 30 volt by using a new polarized aluminum graded undoped AlGaN EB electron blocking mechanism in UVB LED operating under 260 milliamps, or even 500 milliamps was low. And the efficiency droop was remarkably suppressed. Before to say thanks to all of you, but I will just briefly, that's as I mentioned, that we have several ways to improve the external quantum efficiency, internal quantum efficiency, carrier injection efficiency, and light extraction efficiency. So internal quantum efficiency can be improved by this ELO structure to grown on the striped sapphire substrate. And recently we got a very low dislocation density, 1 to 10 power 6 per cubic centimeter in this area. So we need to improve. And also if we introduce the superlattice structure under the buffer layer, we can enhance the IQE by combination of these two things. And finally, the p-AlGaN whole source layer is not enough, we believe that. So we need to introduce p-type hexagonal boron nitride on the p-AlGaN whole source layer because it is bend type 2 material, highly transparent and highly reflective for electron. Electrically, we can reflect back the electron, I mean stop blocking, and a very low accepted energy level in the p-type hexagonal boron is possible, but the epitaxial growth is very challenging. So we also we need to improve the light extraction efficiency by introducing the photonic crystal in this area and also the nano PSS. And recently we got more than 140% enhancement in light extraction by using photonic crystal in UVB LED photonic crystal and nano PSS at the same time. So thank you for your kind attention. And this work was supported by New Energy and Industrial Technology Development Organization, Japan. Thank you.